Hi everyone, thanks for tuning in. This is Nate, a Murph synthetic voice, talking to you from Gradient N. In this video we set up and train a voice classification neural net using the audio MNIST dataset, downloaded from Kaggle. The link and reference are in the description box below. The audio MNIST dataset contains samples of spoken digits 0 to 9 from 60 different speakers. We'll start with the fully connected audio MNIST net we built for our previous video, titled MNIST Audio Classification with a Fully Connected Neural Net. For the fully connected net, we renamed the sound files so that NetDesigner could parse their names for data labels. We also used the data for only the first 10 speakers in the dataset. NetDesigner allows us to preview the sound files. The fully connected net has a sound input layer, 2 hidden layers, and output nodes connected to digit 1, digit 2, digit 3, and so on. We're going to add an FFT, a Fast Fourier Transform, to the fully connected net. Fourier transforms break signals into their frequency components, similar to what the cochlea does in our own ears. First, we'll move the input layer to the left a little. Then we'll move the net to the right. And delete the connections between the two. Then we'll place a process node. And route it. We'll select the process editor. And select the new process node. And, making sure the FFT option is selected, we'll set the FFT size to 128. The data stride to 16. And the downconvert rate to 16. When we add an FFT to our net, we'll be sweeping the FFT across our waveforms and training our net to the FFT outputs. We can set our FFT size, which, along with our original data sample rate and downsample rate, set the net frequency range. We can also set our stride, the increment we use to step the FFT across the waveform data. For clarity, we are showing a stride larger than the FFT size in our diagram, but we usually want a stride equal to or smaller than the FFT size, so there is overlap between FFT samples. The audio MNIST waveforms have a sample rate of 48,000 Hz, and using a downsample rate of 16 gives us an FFT sample rate of 3,000 Hz. We can calculate FFT frequency step size by dividing downsample rate by FFT size. In our case, with an FFT size of 128, we have a step size of 23.4 Hz and a frequency range of 23.4 to 3000 Hz. We're going to grow our net so it can learn all the data from the FFTs, and so we'll zoom out a little to fit the added nodes. Then, we'll copy some nodes and paste them to extend our hidden layer widths. Then we'll move our output layer out a little bit. Erase its connections. Copy and insert an additional hidden layer. And connect everything together. Finally, we'll double-check that the activation functions of our hidden nodes are tan-H, and that our output nodes are sigmoid. We'll double-check that our validation files are set up, and then start training. Let's display the training graph. And speed through training start up a little. We stop training when it looks like the net has stabilized. Notice that net performance is about the same for the training set and the validation set. We'll open our data output dialog and save the net output data for some post-training analysis. After saving net output data, we can look at the classification matrices and see that, while train and validation performances are similar, overall performance doesn't appear to be very good. Considering that the net is time-based, following the FFT, it's more helpful to look at time-based performance. If we look at how the net performs for file subject 0110.wave, we can view net outputs for each digit in the upper stacked area graph compared to the actual sound waveform in the lower graph. In the upper graph, each color represents a different digit. Digit 1 is blue, and we can see that it dominates across most of the waveform. We can see similar performance for digit 2, in orange. For digit 3, in gray, we can see that the net performs okay in the voiced region of the waveform, but not very well in the unvoiced region. 4, in yellow, is identified clearly in the voiced region. 5, in light blue, is also identified clearly in the voiced region. For 6, in green, the net is identifying the S portions of the waveform well, possibly because both the S and X contain the S sound. The net does a good job selecting the voiced sounds in 7, in dark blue. 8, in burnt orange, is picked up a little in the voiced region, but the net doesn't perform very well otherwise. The T sound at the end of 8 is predominantly identified as a 6. 9, in gray, is identified well by the net. For 0, in brown, the voiced E is confused some with 3, and the R is confused with 4. Overall though, the net does reasonably well. When looking at the performance of the net over time, we can see that it has been able to isolate sounds or phonemes that are unique to each digit and identify them well, but fails when sounds in digits are ambiguous with those in other digits. For our next video, we'll add a convolution to the FFT output to see if we can improve performance. Adding a convolution should allow the net to combine multiple FFT outputs together for better generalization across waveforms. Thanks for watching, we'll see you next time.